What's up guys, it's Simon Fiaz and today's video is on Specimen aka level chemistry paper 1. Question 1. Explain how the electron pair repulsion theory can be used to reduce the shape and the bond angle in PF3. So stage 1, electrons around P. P has 5 electrons in its outer shell, with 3 electrons from fluorine, total of 8 electrons in outer shell. So 3 bonding pairs, 1 lone pair. Stage 2, electron pair repulsion theory. Electron pairs repel as far apart as possible, and I also know lone pairs repel more than bonding pairs. So electron pairs repel as far apart as possible, and lone pairs repel more than bonding pairs. Stage 3, conclusions. It's got a tetrahedral shape with bond angle of 109.5 degrees, decreased to 107 degrees because of that lone pair of electrons, which decreases bond angles by 2.5 degrees. Oh no, 2.5 degrees. Say the full electric configuration of cobalt 2 ion. Two 2s, 2p6, 3s, 3p6, 3d7. See, suggest one reason why electron pair repulsion theory could not be used to predict the shape of the CLCl 42 minus sign. Too many electrons in d orbital / d subshell. Predict the shape of the bond angle in a complex rhodium ion RHCl42 minus. Tetrahedral bond angle therefore is going to be 109.5 degrees. Too many electrons in the d orbital / d subshells. Explained by atomic radii of the elements decrease across period from sodium to chlorine. So what you need to talk about in this case is the nuclear charge is increasing whilst the shielding is staying the same. The number of protons across period / nuclear charge increases. Therefore, the attraction between nucleus and outer electrons increases, plus similar shielding across period 3. That's not really that important. Experiment multiplier sulfur is greater than that of phosphorus. Okay, sulfur and phosphorus. Well, sulfur, what is it? It's not macromolecular, that's silicon dioxide. So sulfur, we're just going to talk about the idea that it's got more electrons. Actually, we just say sulfur molecules are bigger than phosphorus molecules. Hence, van der Waals forces between sulfur molecules are stronger. So the way I approached this part was like, okay, sulfur and phosphorus, I know both of them are simple covalent or molecular, so I can't really talk about that. Like I thought it would be macromolecular for van der Waals, but I was like, no. So what I'm going to have to talk about is the amount of electrons, aka sulfur molecules, are bigger than phosphorus molecules. Therefore, the van der Waals forces are just going to be stronger. Number of protons increases, traction, nucleus outer electrons increase. Explain why sodium oxide forms an alkaline solution when it reacts with water. Sodium oxide contains O2 minus ions, and these O2 minus ions react with water forming OH minus ions, so therefore forms an alkali solution. Sodium oxide, O2 minus ions reacting with water to form OH minus ions. Given the equation right, anionic equation of reaction phosphorus oxide with excess sodium hydroxide. Solution P4O10 plus 12OH minus 4PO43 minus plus 6H2O. And is this in the textbook? Paired 3 elements and oxides. It is not. Question 3, I can't do that. Standard electron potential data, no. Can't do that. Question 4, yes, I can do that. Many chemical processes release waste products, blah 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 blah. Using enthalpy change for the reaction data from table 2, calculate value for HH bond enthalpy. Mean bond enthalpy. Mean bond enthalpy is the bond enthalpy required to break 1 mole of bonds in gaseous state over a range of compounds. So let's get down the definition. Just to recall the definition. Mean bond enthalpy is the enthalpy to break 1 mole of bonds in gaseous state across a range of compounds. So in this case, delta H is minus 49. Mean bond enthalpy, energy required to break bonds minus energy released from new bonds and forms. Required to break bonds, C to 1 to O, carbon dioxide, so 743 plus 743 plus 3H2. Well, that's what I'm trying to find. So 3Y minus CH3OH. Now I draw that out. CH3 OH. So I've got CH times by 3. So 412 times by 3 plus CO 360 plus 463 plus H2O. Well, H2O is water, and it's going to be just OH, so 463 plus 463. So minus 49 equals 1486 plus 3y minus 412 times by 3 plus 360 plus 463 plus 463 plus 463 2985. I get 483 kilojoules per mole to power minus 1. Perfect. So just one reason why this value is different from your answer to question 4.1, 436, and I got 483. Reason being that mean bond enthalpies, because that's for the bond enthalpy data book value, I worked out the mean bond enthalpies are not the same as the actual bond enthalpies in carbon dioxide. So just one environmental advantage of manufacturing fuel by this reaction. The carbon dioxide produced is used up in this reaction. Use Le Chatelier's principle to justify why the reaction is carried out at high pressure rather than atmospheric pressure. Well, if I look at this reaction, a high pressure is going to shift to the side with fewer moles of gas, which is the Right hand side. Okay, so that's all I've got to talk about. So I'd say 4 moles of 4 moles of gas forms 2 moles. High pressure equilibrium shifts to the side with fewer moles of gas, aka the right hand side or the forward direction, to oppose the increase in pressure, and decreasing pressure. This increases the equilibrium yield of methanol. 4 moles of gas forms 2 moles. High pressure position equilibrium is at the right. Lower the pressure, increasing the yield of methanol. Suggests that a catalyst used in this process may become less efficient if the carbon dioxide and hydrogen contain impurities. Impurities block the active sites. Question 4.6, calculate a value for Kp. So first thing I would do is I would construct the expression for Kp. Partial, this is the only part. Yeah, turn over for the next question. Okay, perfect. So partial pressure of methanol products times by partial pressure of H2O over reactants partial pressure of carbon monoxide times by partial pressure of hydrogen. And the special thing about hydrogen, we've got 3 moles of it compared to 1, 1, 1. So I need to cube the partial pressure of hydrogen. Okay, now what I need to look at is the idea that how do I find equilibrium moles? So I'm going to have to use the ICE method. That's what I'm going to use. I've got carbon dioxide, hydrogen, CH3OH, and water. ICE. I stands for initial moles, C stands for changing moles, E stands for equilibrium moles. Initially, I've got 1 mole of carbon dioxide, 3 moles of hydrogen. After the mixture reach equilibrium, yield of methanol is 0.86. So methanol 0.86. So what have I done to methanol? Added 0.86. So what I'm going to do to water, I'm going to add 0.86, 1 to 1 molar ratio. Whereas on the left hand side, I'm going to minus 0.86. And for this, I'm going to minus 0.86. But because of 3 to 1 molar ratio, I'm going to times that by 3 as well. So 1 minus 0.86, 0.14. And then 3 minus 0.86 times by 3, because 3 moles of it, 0.42. Now I need to find out the total number of equilibrium moles. So 0.14 plus 0.42 plus 0.86 plus 0.86. I get 2.28. So I'm going to write equals 2.28. Now what I need to do is work out a mole fraction and then just times by the total pressure. Obviously the reason it's 7 marks is you need to show each step, but I'll just do it with my calculator because it's a waste of time. So find out the mole fractions. So mole fraction of methanol. So 0.86 divided by 2.28 is 2. Yeah, it must be 2.28. It can't be 22.8. 2.28 times by partial pressure is mole fraction times by total pressure 500. And remember, I'm just using Kp now. The partial pressure is mole fraction times by total pressure times by H2O, which is the mole fraction of that, or the moles of equilibrium moles of that, 0.86 divided by 2.28 times by 500 divided by mole fraction of carbon monoxide times by total pressure. Carbon, it's not carbon monoxide, it's carbon dioxide. 0.14 divided by 2.28 times by 500 times by hydrogen 0.42 divided by 2.28 times by 500. And remember, with hydrogen, we've got 3 moles of it, so it is cubed. I get Kp as 1.48 times by 10 to the power minus 3. The units, well, I didn't convert it into pascals, I used kilopascals. It's going to be kilopascals times by kilopascals squared, over kilopascals times by kilopascals cubed, kilopascal to the power 4, which is the same as 1 over kilopascals squared, and that is the same as kPa to the power minus 2. So that's going to be my units, kPa to the power minus 2. Does it want it to appropriate number of significant figures? I guess I could do 1.5 times by 10 to the power minus 3. kPa to the power minus 2. Calculate equilibrium moles, calculate total number of gases, calculate partial pressures, but the partial pressures I just substitute in the calculator. Obviously, you need to show in the exam, that's why it's 7 marks, all of those. Partial pressures, mole fraction times by total pressure, and then you get Kp by just substituting the Kp expression. That's why first thing I did was write down the Kp expression, so then I don't need to do it later on. Question 5. Use this enthalpy change and data from table 2 to calculate a value for the free energy change of the reaction at 250 degrees Celsius. Give units with your answer. Alhamdulillah. Alhamdulillah. So, all I need to do first is I need to find out entropy change. It doesn't give me that, does it? No. If it did, then it wouldn't be worth 4 marks. So entropy products, I don't think, minus entropy of reactants. Okay, so it's just going to be entropy of products, CH3OH, 238, plus this H2O, 189, minus entropy of reactant, 214, plus, I've got 3 moles, so plus 131, plus 131, plus 131. That'll give me 238 plus 189, 238 plus 189, 427, minus 214 plus 131 plus 131 plus 131, 607, 427 minus 607, 1 minus 180. Remember, with entropy changes, joules, K to the power minus 1, mole to the power minus 1. It gives it in the question as well here in the table data. Now I already know delta H, so now I can already find out Gibbs free energy change. Delta G equals delta H minus T delta S. I've got delta H, which is minus 49 in kilojoules mole to the power minus 1, minus the temperature in degrees Celsius. I need it in Kelvin, so I need to add 273, 250 plus 273, 523 Kelvin. So minus 523 times by delta S entropy change minus 180. And here's the tricky part. I want my Gibbs free energy change. I need to divide this by 1000, I think. Yeah, I need to divide by 1000. So minus 180 divided by 1000. 523 times by minus 180 divided by 1000, and I get 45.1. So positive 45.1 units kilojoules mole to the power minus 1. So find out delta S, minus 180 joules K to the power minus 1 mole to the power minus 1. Delta G is delta H minus T delta S. Delta H is in kilojoules, therefore I need to convert delta S in kilojoules by divided by 1000. Then substitute in temperature, I need temperature in Kelvin, so add 273 to degrees Celsius to convert to Kelvin, 523. Substitute in there, you get delta G and obviously the units can be kilojoules mole to power minus 1 since I converted both of these. Delta H was already in kilojoules mole to power minus 1. I converted delta S to kilojoules mole to power minus 1. Therefore, my units for Gibbs free energy change will be in kilojoules mole to power minus 1. 5.2 calculate temperature for the reaction when the reaction becomes feasible. So when the reaction becomes feasible, delta G equals 0. So delta G equals delta H minus T delta S. And I just said when the reaction becomes feasible, delta G is equal to 0. So it's going to be 0 equals delta H minus T delta S. Rearrange to get T equals delta H minus delta S, which is just going to be minus 49 divided by minus 180 10 by 10 to the minus 3. Because I want my temperature in Kelvin. So minus 49 divided by minus 180 10 by 10 to the power minus 3. I get 272 Kelvin. The key part to memorize is when when temperature just becomes feasible, delta G is equal to 0, rearrange it. Gaseous methanol from this reaction is liquefied by cooling before storage. Draw a diagram showing the interaction between two molecules of methanol. Methane, ethane. So I've got two lone pairs of electron delta negative. Got the same thing here. Two lone pairs of electrons delta negative, oxygen delta negative. This hydrogen delta positive. And then what happens is, I don't need to include that delta negative. There you go. Explain why this methanol is easy to liquefy. Hydrogen bonding is a strong enough force to hold methanol molecules together in a liquid. It's easy to liquefy because of hydrogen bonds. It's strong enough, very strong, to hold the methanol molecules together in a liquid. Question 6. Question 7. Question 8, I can't do question 8. Ligands, transition map 9, I haven't gone through that in class. Question 9, I can probably do. Question 10. No, I don't think I can do that. So question 9. Question 8, no. Question 9. And we'll have a look at question 7, but I'm not sure about that one. So question 6. So ammonium chloride when dissolved in water can act as a weak acid, shown by the following equation: acid and bases. Suggest a suitable piece of apparatus used to measure a sodium hydroxide solution. Burette. Burette, because it can measure variable volumes. Actually, no, because it can deliver variable volumes. Then it says, using information occurred, explain why the endpoints of action were difficult to judge using an indicator. So the endpoints of action like here, very gradual. The change in pH is too gradual / not rapid at the endpoint. Hence, an indicator would change color over a range of volumes of sodium hydroxide. An indicator would change color over a range of volumes of sodium hydroxide, but the change of pH is too gradual / not rapid at the endpoint. The pH is that Use pH value in ionic particle water to calculate concentration of hydroxide ions at end point of reaction. So I'm going to be using Kw, ionic product of water, is equal to concentration H plus divided by concentration OH minus. I'm going to find pH. Okay, so wait. Yeah, I know. I want to find out concentration OH minus ions. Equals Kw divided by concentration H plus ions. How to find concentration H plus ions is 10 to the power minus pH. 10 to the power minus pH. Therefore, it's going to be 10 to the power minus 11.8. So it's going to be 1.0 times by 10 to the power minus 14 divided by 10 to the power minus 11.8. And that will give me the concentration of hydroxide ions. That's simple. Uh, 6.31 times by 10 to the power minus 3. What was it again? 6.31 times by 10 to the power minus 3. Mole per d minus cubed. So just find out H plus 10 to the power minus pH, rearrange Kw expression ionic product of water, get OH minus ions. That's it. Expression for the acid dissociation constant for aqueous ammonium ions is that the initial concentration of the ammonium chloride was that. Uses pH before any sodium hydroxide had been added to calculate the value of Ka. So I know that initial concentration of the ammonium chloride was 2. I want to use a pH before any sodium hydroxide be added. So look back at the graph before. So when 0 volume of sodium hydroxide is being added, what is going to be the pH? Well, I just look here, and that's going up to 4.2, 4.4, 4.6, 4.85. So around about 4.6, I would say. Yeah. Yeah, definitely 4.6. So pH equals 4.6. Why is that useful for me? Now I can find a concentration H plus ions, which is 10 to the power minus pH, which is 10 to the power minus 4.6. And then I can also say before any sodium hydroxide solution has been added, so pure, therefore concentration H plus equals concentration A minus. Or I could say concentration NH3 equals concentration H plus. Obviously applied to the question in exam. So I'm going to rearrange, so I can say Ka equals concentration H plus squared divided by concentration HA. Therefore, concentration H plus. No, I want to find out a value for Ka. Sorry, read it wrong. So KHA. No, I want to find a value of K. So all I do now is substitute my values in 10 to the power minus 4.6 squared divided by 2.00. A lot easier than I thought. I thought it'd be rearranging as well. 2 minus 4.6 squared divided by 2.00. 3.15 times by 10 to the power minus 10 moles per t minus q. 3.5 times by 10 to the power minus 10 moles per t minus q. A solution contains equal concentration of ammonia and ammonium ions. Use the value of Ka to calculate pH of the solution. So contains equal concentration of ammonia and ammonium ions. So that's fine. Well, therefore Ka equals concentration of H plus squared actually no, equal concentrations of ammonia and ammonium ions. So ammonia and ammonium ions. Oh right, okay. So Ka in the given equation equals NH3 AH plus NH4 plus, right? And it tells me in the question, in this question part, equal concentration ammonia and ammonium ions. So they basically cancel out since it's equal. Therefore, I'm left with Ka equals concentration H plus ions. and I've got Ka. Find the pH. Minus log 10 Ka equals minus log 10 of H plus. Therefore, the pH is just going to be minus log 10 of Ka. So minus log 10 of 3.5 times 10 to the power minus 10, 9.46. Oh, it's 3.15. Yeah, it's 3.15 times 10 to the power minus 10. I said 3. How did I get 3.5? That's a good question. 10 to the power minus 4.6 squared divided by 2 divided by 2. It's 3.15. So again, it's a silly mistake. I just forgot to write the 1. And then yeah, you should get 9.50 to 2 decimal places. But yeah, just identify equal concentration of ammonium. Ammonium ions cancel out K because H plus, then therefore pH equals minus log 10 of Ka. Which is 9.50 using this answer Ka. Question 7. I don't know if I can do this, but I definitely can't do this different oxidation states and calculate oxidation state of that. No. I know it's PV because I know T a bit of it, but then the rest of it I won't be able to do that. So no. Question 8 I can't do, and then therefore I'm just left with question 9. So I'll have a look if I can do these little 1 markers that are here. I think I know how to do it. It says which element is calcium, and it gives us a successive ionization energy data X, Y, and Z. Well, if it's calcium, well, I need a periodic table for this. I'm going to have to use this method. So I need a periodic table. So I need a periodic table. Okay, got it. Periodic table. Okay, so element calcium, Ca, is in group 2. Group 2. Vanadium is in group vanadium is in group which is in period 3. Okay, anyway, and then so which element is calcium? Well, calcium, X, Y, and Z, the massive jump in ionization energy has got to be from the second one. Let's move from the second one. Calcium is going to be Y, and vanadium is going to be X. Just the right choice of vanadium in question 7.2. Jump in trend of ionization energies after removal of fifth electron. Fits with an element with 5 outer electrons. Right, yeah, I don't get that part. I haven't gone through it. I don't think. And then question 9. Describe the steps to determine accurate minimum temperature that is not influenced by heat from the surroundings. This is practical skills then, in this case. So, start a clock when KCl is added to water. Record the temperature every subsequent minute for 5 minutes. Plot a graph of temperature versus time. Extrapolate back to time of mixing equals 0 and determine the temperature. You either know what you don't. It's practical skills. You need to memorize these off by heart. What you have to do. The temperature decreased to 14.6 degrees. Calculate a value for the entropy of solution of potassium chloride. And then these questions. So it says, so Q equals, first I'm going to write down all the equations that could be possibly running. Q equals MC delta T. Delta H equals Q divided by moles. So what I'm going to do is I'm going to do Q equals the mass, this case of water, 50 grams. So 50 times by 4.18 C times by temperature of water decreased to 14.6 degrees. And initially it was 20 degrees. Oh, okay, so that's what I have to read back. So it's just going to be 20 minus 14.6, which is 5.4, and therefore that is delta T. Final temperature, my initial 20 minus 14.6, 5.4. That will give me Q. Now I need to find out the moles. Well, moles is mass over mR, and in this case the mass is the mass of the alcohol, but in this case it's going to be the mass of, not the water, of potassium chloride, and should be given in the question 5 gram sample, perfect. So it's going to be 5 divided by the mR of potassium chloride, 74.6. Then to find out delta H, the entropy is just going to be Q, what I worked out here, divided by the number of moles, energy change per mole, which will give me 16,839 joules per mole to the power minus 1. Because remember, specific heat capacity in joules, K to the power minus 1. I want in kilojoules, so it's going to be 16.8. And it's obviously going to be positive. Make sure you do that as well. Just temperature decreases 20 degrees to 14.6. Decreases, therefore, it's endothermic. Temperature increase from 20 to 40.2. Then it'd be negative exothermic. Entropies of solution calcium chloride is minus 82.9. Entropies of hydration for calcium ions and chloride ions are minus 1650 and minus 364 respectively. Use these values to calculate the value for the lattice entropy of dissociation of calcium chloride. So calcium chloride solid, and I go to Ca2 plus aqueous plus 2Cl minus aqueous, and I've got Ca2 plus gaseous plus 2Cl minus gaseous. What do I want to find? Entropy lattice dissociation. calcium chloride. So it's not this. This is minus 82.9 enthalpy of solution. Then I go down, then I go up. Enthalpies of hydration of that. So what I want to find, lattice association, I want to find this basically. Say that's X. Calcium ions, hydration of calcium ions minus 1650. Hydration of chloride ions minus 364 respectively. But think about chloride ions, I've got 2 moles, so I need to times it by 2. So what I'm going to say is I'm going to say minus 82.9 this way equals X plus, I'll say Y, don't want to get confused between X and all that, Y plus minus 1650 minus 1650 plus minus 364 plus minus 364 minus 2378 minus 82.9 plus 2378 2295.1. Let's go. 2295 kilojoules per mole to power minus 1. And then 9.4, explain why the answer to question 9.3 is different from the lattice enthalpy of dissociation from magnesium chloride. Magnesium chloride, lattice enthalpy of dissociation from magnesium chloride. Why is it different? Well, what's the difference between magnesium chloride and calcium chloride? Well, calcium. Okay, so what I'm gonna have to say is that Ca2 plus ions are bigger than Mg2 plus ions. But I want to know why it's different from the rest. Oh, I say actually, in this case, Mg2 plus ions are smaller than Ca2 plus ion, hence attracts, because magnesium chloride, Mg, and chlorine, it attracts a chloride ion more strongly, hence stronger ionic bonding. Or I guess we could say Ca2 plus ions are bigger than Mg2 plus ions, hence attracts the chloride ions, because it's calcium chloride, yes, actual chloride ion less strongly, hence weaker ionic bonding, the opposite of that. But yeah, you should say this, not the other part I just did. Mg2 plus ions are smaller than Ca2 plus ions, hence stronger attraction for the attracts the chloride ion more strongly, hence stronger ionic bonding. And that is the end of this paper.